We're going to continue talking about electrons today, specifically electron configuration. Last time we talked a little bit about electrons, light, and waves, and you saw some of the relationships between variables such as wavelength and frequency, energy and frequency, energy and wavelength. And hopefully you feel very comfortable with that type of problem solving. We can explore that in the second half today if you need more help. Last time we also talked about how electron position was determined. We talked about Bohr's model with electrons in orbits, and then the quantum mechanical model where electrons are actually in orbitals. What we're going to do today is write electron configurations for elements. Today only in the ground state, next time in the excited. And we're also going to draw orbital diagrams, and we will interpret both electron configurations and orbital diagrams. It looks hard because it's like nothing you've ever seen before, but I promise with a little bit of practice you'll be very good at it. All kids are very, very good at writing electron configurations. And this will be the crux of your quiz tomorrow. So last time we finished up with quantum numbers, and we'll link that back today so you can see the relationship between quantum numbers and electron configuration. We're going to learn how to write electron configurations and then to draw them. Before we do so, we want to go over a couple of principles and rules that help explain why electron configurations are written the way they are. The first principle is Pauli's exclusion principle. It says that only 2 electrons can occupy a single orbital. Remember, an orbital is a region in space where there is a 90% chance that the electron will be located. You can calculate the energy of an electron, but there's only a 90% probability that the electron will be there. Orbitals come in 4 different shapes: S, P, D, and F. In each orbital, you can only have 2 electrons, and if there are 2 electrons in that orbital, those electrons must spin in opposite directions. So for example, and this will become clearer in about 10-15 minutes, if this circle represents an orbital, within each orbital you can have a maximum of 2 electrons. The electrons must spin in opposite directions. So typically I show that by arrow up and arrow down. This is an electron. This is an electron. Their spins are different. Their m sub s values. This one would be -0.5, and this would be +0.5, and that's how you can differentiate electrons that are in the same orbital. Pauli's exclusion principle says you can fit a maximum of 2 electrons in an orbital, but the electrons must spin in opposite directions. Now, I usually use circles to represent orbitals. Some people use boxes. Some people use lines. I'll show you all the different ways. Pauli's exclusion principle. Aufbau's principle is the second rule. It says electrons in an atom will occupy the lowest energy orbitals available. This is the video game rule. For example, I don't know, we used to play Tetris and Donkey Kong and Super Mario way back when. You guys play Call of Duty and some of these other fascinating, mind-blowing games. But you have to complete level 1 before you go to level 2, then level 2 before 3, level 3 before level 4. Same thing in school. You go to kindergarten, 1st grade, 2nd grade, 3rd grade, 4th grade, etc. Aufbau's principle says electrons will be placed in the lowest energy orbitals available. You must fill a sublevel before going to the next. This is a little bit tricky because it's not just the n equals 1, 2, 3, 4, 5, 6, 7 that we talked about previously. You'll see what I mean by increasing sublevel when you write it, and I'll point that principle out to you. We'll refer back to these principles when we write the electron configurations so they make a little more sense. Hund's rule. Hund's rule says that orbitals within the same subshell, that is to say, if you had subshell 2p, you're going to see the quantum number link in a minute. You would have 1, 2, 3 orbitals, and I'll show you how to figure this out in a few minutes. It says orbitals within the same subshell are each occupied by one electron with the same spin before pairing occurs. This is the bus rule. For example, let's say that this is my little mini bus. Doesn't even have a driver. It has 5 seats. And the football team just won their game, and they have lots of these buses, and 8 kids are getting on this bus. 8 big, 300-pound, sweaty football players. First kid gets on. He sits right here. When the next kid gets on, does he want to sit in the seat with him? No, those seats are so little. Those football players are so big. He's going to take his seat right here. And then the next one, and the next one, and the next one. Now, when football player number 6 gets on the bus, he has no choice but to pair with somebody already in a seat. But he has to sit in the opposite direction. I don't know if you do this anymore at sleepaway camp, but when we went to sleepaway camp, we used to sleep head, toe, head, toe. Anybody ever go to sleepaway camp? No? Did you sleep head, toe, head, toe? Did you sleep head, toe when there was lice? Oh, think of what you missed. Well, at camp, the counselors used to always go out partying, and they'd come back, and they'd always bring lice back. And as a result, all the kids would get it. So to prevent some of the lice from jumping from head to head, we used to sleep. This person's head is here, and this person's toes are here. That's what I mean by head, toe, head, toe. So it's the same concept here. When the 7th player gets on the bus, he sits here, here, and then not all the seats are filled up. Each electron is placed in an orbital of the same subshell until pairing has to occur. I'll illustrate that more when we draw it. But those are your 3 principles. Pauli's exclusion principle, a maximum of 2 electrons in an orbital. They must spin in opposite directions. Aufbau's principle says you fill a sublevel before moving to the next. I'll illustrate that for you when we write and draw. Hund's rule is the bus rule. All right, keep those in mind. The steps we're going to follow to write an electron configuration, I'll mention here, but until we do it, it's not going to come together. Have a little patience with it. I know you're the smartest kids in the school, and you're used to understanding everything right away. Give it a good 15 minutes to develop, and I promise you, you'll be able to do this with great success. It says determine the number of electrons to appear in the electron configuration. If you know the atomic number for an element, then you know not only the number of protons, but also the number of electrons, because atoms are electrically neutral. Once you know how many electrons there are, now you're going to figure out how to write the configuration. You list subshells in increasing order of energy. You can use the subshell tree diagram shown right here. Now this diagram is provided to you on the back of your periodic table. Unfortunately, not all the arrows came out clearly, so you may want to write them in. I've got a little subshell tree diagram here. It just has colors, so we're just going to use this one to explain it. It says follow the arrows which show increasing energy. Your start point is here. You must follow the arrows, you must follow the arrows, you must follow the arrows, you must follow the arrows. If you don't follow the arrows, and there's always one kid in each class who doesn't, you will not pass the quiz. Follow the arrows, follow the arrows, follow the arrows. So in looking at this, what you have, this is your start point. 1s is the first subshell. Follow the arrow, then 2s, then 2p, then 3s. Increasing energy following the arrows. After 3s is 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 7s, 5f, 6d, 7p. So it's not based solely on the n value. This shows increasing energy level. You must follow the arrows. You'll note that 4s is of lower energy than 3d. Follow the arrows. You will use superscripts to represent electrons, and you'll place them according to Pauli's exclusion principle and Hund's rule. That is more apparent in the orbital diagrams that I will show you. When drawing orbital or energy diagrams, I typically use circles to represent orbitals. You can use lines or boxes, whatever you want. I'll show you everything. And you'll use arrows to represent electrons, making sure they have opposite spins as we illustrated. We said the other day that there are 4 different orbital shapes. When we're looking for how many orbitals there are per subshell, and again, this term is a little bit tricky. S, P, D, and F is going to be your orbital shape. This is a sublevel. You've got the N and the L. These are orbitals. The nomenclature is a little tricky. When you're considering how many orbitals there are in a subshell, or for S, P, D, or F per se of that subshell, the number of orbitals per subshell is equal to 2L plus 1. So that's the number of possible M sub L values that we mentioned the other day. So what is L for S? 0. 2 times 0 is? Plus 1 is? What is L for P? What's 2 times 1 plus 1? And that's where these numbers come from. L for D is 2. 2 times 2 plus 1 is 5. L for F is 3. 2 times 3 plus 1 is 7. So the number of possible M sub L values is how many orbitals or circles you have for subshell.
So 2 times M sub L plus 1.
2 times L plus 1 is equal to the number of possible M sub L values. And that's from Monday that probably didn't quite click yet, but when we do the classwork today, you'll be golden. All right. Now, Pauli's exclusion principle says you can fit a maximum of how many electrons in an orbital? 2, but they have to spin oppositely. So to figure out the maximum number of electrons per orbital set or subshell, you're just multiplying these values by 2. So what you're going to see here is that S can hold a maximum of 2 electrons, P can hold a maximum of 6, D can hold a maximum of 10, and F can hold a maximum of 14. So this is the maximum number of electrons in that subshell. And now I want to show you how to write them. And again, the subshell tree diagram here is in your notes. I did put it directly on your quiz to make life easy for you. I will tell you, you should modify your back of your periodic table slightly if it's not clear. I had made a dashed line and unfortunately it didn't Xerox well. So you may want to go through with a pencil. So you've got it, but be comfortable with it because your laminated periodic tables unfortunately show that too. I don't think it's a big deal. Follow the arrows. I'm going to show you how to write a few. I'm going to walk you through very, very closely. We want to write electron configurations. We want to draw orbital diagrams. We want to interpret them. Not hard. Just like everything else, it requires practice. If you practice, you will be solid, provided that you follow the arrows. And I know I've said that probably 10 times, but trust me, gotta follow the arrows. In your notes, it says we want to write electron configs and draw orbital or energy diagrams, and this will show how electrons are distributed within a sublevel. We're going to write electron configurations, and we're going to draw orbital diagrams for most of the elements listed here. We'll do as much as you need. If you need more, we'll do more. And then there's a few things I want to illustrate based on our drawings. The first one we want to draw is fluorine. And I'll keep this subshell tree diagram here for you so you can use it. When you actually fully understand this, you don't need it. But right now we do. So fluorine has an atomic number of 9. How many electrons does fluorine have? 9. First thing we figure out. Now we're going to use the subshell tree diagram. Our starting point is 1s. So we're first going to write the electron configuration for fluorine. We have 1s. How many electrons can you fit in an s orbital, or in this case it is the subshell? 2. After 1s comes 2s. How many electrons can we fit in an s? 2. We've placed 2 plus 2 is 4 electrons. We need a total of 9. What comes after 2s? 2p. Now p can hold 6, but how many do I need to place to get to 9? 5 is correct. Those superscripts have to add up to the number of electrons. That's an electron configuration. The orbital diagram shows the electrons in orbitals. We have increasing energy here. The sublevels as written show increasing energy. I'm going to use a circle to represent an orbital. My first orbital is 1s, and that comprises the entire subshell. Next up is 2s, and it is of higher energy, so I'm making it right here. The circle should really be the same size. I got a little circle happy. Now for 2p, how many circles should I have? For S you have 1, for P you have 3, for D you have 5, and for F you have 7. So this one needs 3, and it's slightly higher energy. So this is a subshell. This is a subshell. This is a subshell. Now I'm ready to place my electrons, and I can emphasize those rules now. In the first subshell 1s, I have 2 electrons. Arrow up, arrow down. That's Pauli's exclusion principle. You fit a maximum of 2 electrons in an orbital. They must spin in opposite directions. Aufbau's principle says I fill the sublevel before moving to the next. So now I've got this one, arrow up, arrow down. Now here's the tricky part. Sometimes this is thought of as the px, the py, and the pz orbital, because this one's oriented around the x-axis, the y, and the z-axis. The sublevel is full. I move to the next one. That's Aufbau's principle. Hund's rule is the bus rule. You put 1 electron in each orbital of a subshell before you pair. You go, look up at the screen. You go up, 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 down, down. Okay? Now when you draw your electrons, like I said, some people will use lines to represent orbitals. They'll want arrow up, arrow down. Doesn't matter to me how you do it. Some people put these in boxes instead of lines. The only thing I will say is don't do this. That looks like something on Peanuts and you're not going to get credit. Don't do this. They're not spinning in opposite directions. That violates Pauli's exclusion principle. Don't do that. So you can do this. You'll see all my work looks like this. Can't see anything. I made it so big. Sorry. So you can do this. You can do this. You can't do that. That's the Peanuts character stuff. That's like blah, 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 blah. You guys probably don't watch Peanuts, but it's so cute. You can't do arrow up, arrow up. That violates what? Pauli's exclusion principle. Can't do arrow down, arrow down. That too violates Pauli. Alrighty? couple questions you could be asked, and that's why this chapter can be a little tricky, but I'm going to try and give you every variety of question that you might see on your test next week. Your quiz is very straightforward. First question you might be asked: how many unpaired electrons how many? That guy right there, he's an unpaired electron. How many electrons in the second shell? Careful. The second shell is where n equals 2, right? N equals 2 here and here. So you could even look up here, and how many electrons in the second shell? 7 is correct. We're going to do a lot of this, so don't worry. It's really kind of fun. Let's do another one. Are you with me? Alrighty. The next one is phosphorus. Phosphorus has an atomic number of 15. How many electrons? 15. Alrighty. Raise your hand if you want to do it with me. Who wants to draw? Who wants to write it with me? Okay, go ahead. You're Ashley, right? Yeah. Okay.
So the first one would be 1, 2.
Okay.
Then 2s, 2p, 6.
And we've placed 10 so far.
3s, 3p, 3.
That is correct. The superscripts have to add to the number of electrons. All right. When drawing the orbit, so that's the electron config. When drawing the orbital diagram, and the orbital diagram question I give you will be pretty straightforward because you could make circles and drive yourselves nuts. Yes?
So when you use the subshell tree diagram, do you keep going until you get the amount of electrons?
Exactly. Alrighty. So again, this shows increasing energy. This one I'll continue to draw up so it further emphasizes the increasing energy of the sublevel. But when you go to draw it, you're probably just going to draw a string because it'll be easier for you. Just label it. Yeah, I'll do that for ones that have more because it starts to be like, you know, just goes and goes and goes. Like the Energizer Bunny. All right, so we've got 1s. We've got 2s. We've got 2p. We've got 3s. And then we've got 3p. And again, each time you've got the N and the L, you have a subshell. Arrow up, arrow down, arrow up, arrow down, arrow up, 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 down, down, down. Be careful when you have more than one orbital in a sublevel. Don't disobey Hund's rule. Arrow up, arrow down. And now be careful. Hund's rule says you must put one electron in each orbital of a subshell, spinning in the same direction, which will be up before pairing occurs. 1, 2, 3. Several questions that we can ask. And I'll abbreviate it for you so you don't have that much to write. We want to know the number of unpaired electrons. What would that be? 3 is correct. I want to know the number of electrons in the first shell, second shell, and third shell. How many in the first shell? 2. How many in the second shell? 8. How many in the third shell? In middle school, do you remember learning something with 2, 8, 18, and 32? I'll show you where that comes from. You're seeing the 2 and the 8 right now. Maximum number of electrons in the first and second shell, respectively. Questions on either of these? So it looks really hard, but it's going to be easy for you. Yes?
How would you have the electrons in the subshells?
In the subshells or the shells?
Shells.
Shells. So for example, in the first shell, N is 1 and there's 2. In the second shell, N is 2 and there are 8. In the third shell, where N is 3, there's 5. Now, I don't always love to do this, but I'll show you guys because you're really smart. If you look here, you can figure out shell by reading from left to right. First shell, second shell, third shell, fourth shell, fifth shell, sixth shell, seventh shell. But just be careful because if you don't follow the arrows, you're going to crash and burn. All right, let's do another one. Okay. So C is calcium, atomic number 20. 20 electrons. I need somebody to help me write the electron config. Somebody who doesn't feel so good about it. Come on, we'll help you. Go ahead, Haley. I don't know, but you were smiling, so I knew you wanted to be picked.
Okay. 1s2, 2s2, 2p6, 3s2, 3p6, 3s2.
What comes after 3p?
Oh, 4s2.
Good. Excellent. Superscripts add up to 20, followed the subshell tree diagram, golden. In regard to the orbital diagram, this is where I'm not going to keep going up because I'll run out of room. So we'll make it simple. We'll do like 1s, 2s, 2p, 3s, 3p, and then 4s. And again, up, down, up, down, up, 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 down, down, down. That got a little tight there. My circles are really kind of little. Can you see? I think I made them too little. Sorry. Up, down, up, 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 down, 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 up, down. How many unpaired electrons? None. How many electrons in the third shell? Julia.
Oh. 8.
8 is correct. Right here you have 8, right? You got it. There is one thing I do want to mention. I don't see an example here just yet. But if you have an orbital, let's say you had this situation, how many unpaired electrons would you have? 2. This is just an unoccupied orbital. It's like an empty desk. Just because somebody's absent doesn't mean I take the desk and put it in the hallway. So it remains, it's just empty. It still exists. All right, let's do D together, and then I'm going to let you try a couple. D is cobalt with an atomic number of 27. "27 electrons. Raise your hand if you need more practice with me. You'll do it right now with me. Otherwise, I just pick you. Go ahead, Sean.
1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3b7.
That is correct. Excellent. All right. Now, it is important that you can draw the entire orbital diagram as we've been doing. It is a waste of time to redraw all of this. So I'm just going to focus on the last subshell here for you, but make sure you can do all of it. Once you get good at it, just focus on the last subshell. The last subshell written is 3d7. How many circles for a 3D subshell? How many? 5 is correct. Remember, it goes 1, 3, 5, 7. Now we're going to place 7. Hund's rule. Arrow up, arrow up, arrow up, arrow up, arrow up, arrow down, arrow down. How many unpaired electrons? 3 is correct. How many electrons in the third shell? Victoria.
The third shell. 8. 15.
15 is correct. So there are 15 electrons in that third shell. I would like you to try E, which is selenium with an atomic number of 34. And that will be on the screen highlighted in green. And when you're done, you can look up at the screen and I'll show you the answer when you're done. Are you done? I only drew the last subshell because it's just too much to write.
Like for 3D, instead of 10, how do you get that top number?
Because how many D's can you have? How many orbitals for D? It's 5. That's based on the 2L plus 1. So D has an L of 2. 2 times 2 plus 1 is 5. So there are 5 circles for D, and each circle can hold 2. So S can hold 2, P can hold 6, D can hold 10, and F can hold... That's up here. On the screen, this tells you how many it can hold. All right. How'd we do with selenium? Yes, yes? Okay. I do want to make the quantum number leap, if you will. Probably a bit too much for the honors level, but you're super smart. We said that each electron has a unique set of 4 quantum numbers. If we focused on this electron here, what's its N? What's the L? One is correct. The M sub L's go -1, 0, and 1. So this would have an M sub L of -1, and its M sub S would be -0.5. This electron has the same N, the same L, the same M sub L, but a different M sub S. So no 2 electrons have the same 4 quantum numbers. And again, this is, you should be able to get the N and the L with ease, but figuring out all the quantum numbers for an electron is above the scope of the course, but it's interesting. Questions here? Okay, I would like you to try H. I'll let you do F and G when we problem solve, but how about you try H, which is platinum with an atomic number of 78. Give it a shot. H, highlighted in blue. And just draw the last subshell out, because otherwise you'll be making circles for the rest of the day. You good? And then I have some questions for you to answer. We can do them together. Is that what you got? Yes, yes? See, I told you you'd be able to do it. Now you'll believe me. Okay. How many unpaired electrons? 2 is correct. 1, 2. Now, how many electrons in the third shell? Again, anywhere n is 3, 18 is correct. How many electrons in the fourth shell? How many electrons in the fifth shell? Now the fifth shell is not complete, but remember you learned about 2, 8, 18, and 32? Maximum number of electrons in the first, second, third, and fourth shells respectively, and that's where it comes from. Questions here? The last thing I want to mention is just the backward interpretation of it. I don't believe I put this on the quiz, but I know I put it on the test and it goes with it. If you want to figure out the element from the corresponding electron configuration, how might you go about that? Brian? Exactly. Get the sum of the exponents. 2 and 2 is 4 and 3 more is 7. So this has an atomic number of 7. And that would correspond with nitrogen. How many electrons for B? 11, and if you looked at a periodic table, that would correspond with sodium. And then for this one, how many electrons? And that would correspond with titanium. So you could figure out your element from an electron config as well. Questions here? Okay, what I would like you to work on for the second half of class, and you have 55 minutes, which is a lot to really master this before you walk out the door. I do want you to do F and G in your notes, although I think one of those is in the classwork. They may both be in the classwork, so we won't worry about F and G. In your classwork, which you already have, part 1 should be complete because I asked you to do that over the weekend to make sure you had a beat on that. You now can do parts 2 and 3. And your quiz will go through the point we've discussed today. Your quiz will be about 20 minutes. We'll have about a 30-minute lesson, and then we'll have a lab activity to further cement some concepts and get you ready for your last test of the quarter, which will be Tuesday. So in the next 50-plus minutes, classwork 1-4, and you should be able to do parts 2 and 3 in class now so that you're studying a little bit tonight, a little bit tomorrow, and you can ace your quiz on Friday. Questions? You feel like you've got it? I don't know if you can explain it to somebody yet, but I think you can do it, and after this time period, I think you will be able to. All right, good job, guys.